So, welcome to Powering Up Dagger for Less Code and Cleaner Architecture. I'm going to explain what I mean by this in a little bit, but let me introduce myself. I'm Sumayyah. I currently work at Square doing Android things, of course. In between, I also do a bunch of talks at DroidCon and other places, so you can find me on LinkedIn or my blog. Don't look at my GitHub, there's nothing there. Today, we're going to look at Dagger as a code generation tool. Because God knows, there's enough talks about Dagger. Pretty sure everybody here has touched it at some point. So we all know how it works, right? We set up modules, we set up the component, and we inject our dependencies, and then we're done, we move on with our life, which is great. And it works for a lot of use cases, right? That being said, there's a lot of stuff we can do with Dagger that solves architectural issues that pop up in any decently sized Android codebase. So, business problems that you will get when you're building these super app type of things. You have to support this giant app that has multiple users or multiple profiles or multiple accounts, and you're trying to swap back and forth between them. This probably means that you have dependency graphs that you need to switch back and forth between. Dagger's great at supporting this with scopes and subcomponents. Scaling back down a bit, think about things like plugin type of architectures that may crop up in multiple places in your app. You may want multiple modules to provide implementation so that a central class can use that entire set. This is a great use case for multi-binding. So in this talk, we'll do a non-comprehensive look at what Dagger is doing under the hood. And then we'll talk about multi-bindings, how to apply them, and also deal with scopes, subcomponents, and how this helps architecture at the app level. Last but not least, we're going to talk about why to never do any of those things, because the whole point of having a tool is to know when to use it and when not to use it, right? Ask me how I know, because I have suffered many times. So we're going to have about 34 minutes exactly of this talk. And why is it 34 minutes? Is because yesterday, as I was driving into the city and I was 30 minutes away, I decided to rehearse this talk to myself. And I got really into the flow, and 4 minutes before I finished, I missed the exit to the Lincoln Tunnel, and I got right into New Jersey. And so for all of our sakes, I hope it was worth it, because I spent 30 extra minutes on the highway. So the goal of this talk is going to be Dagger for less code, cleaner architecture, happier developers, and easy money. All of this, by the way, applies to Anvil and Hilt, because they're all just compiled onto Dagger. Everything I'm going to talk about today is going to apply just as well. Actually, out of curiosity, how many folks use Anvil in their code base? Oh, that's a decent amount. I see the Square folks. You guys don't count. You have to use it. What about Hilt? Oh, nice. Okay. If you are using Coin or any other thing, I'm sorry, I don't know how this talk will help. You may as well just hang out till the after party. And speaking of parties, let's get on with the talk. How does the Dagger magic work? And really what I'm talking about is the 4 common annotations, right? Provides, inject, component, module, probably singleton as well. And really, what the magic we're talking about is just plain old Java-style annotation processing. And so if you've written a processor before, this is going to look really familiar. At some point in the compile process, there is an annotation processing step where all the processors in your code base, including Daggers, are going to crawl through the source code looking for these particular annotations that they have parsers for. And they're going to write a bunch of code. And so in Dagger's case, it means writing a bunch of factory classes, injector classes, most importantly, the component classes. These are all Java classes that are going to be added to the project. And then compile keeps going, and then you end up with class files and what have you. But really, this is what Dagger is doing at its core. It's just adding a bunch of files into your project. And if you're curious, you can check it out in your generated folder in your IDE, or try to crawl through the app build generated folder somewhere. And for me, it's like Dagger is somewhere in the kapt folder, and if you're lucky, you may have it in the KSP folders. But where you have classes, you're going to have objects, right? So what are these objects that are getting instantiated, and where do they live, and what are they doing, and how does that help with dependency injection? Let's start simply. Let's take a look at the dependencies we instantiate every time we use the provides annotation. Each dependency provided this way gets turned into a factory instance. And by factory, we're really talking about Java's provider class. It's literally just a wrapper that overrides a get function. It wraps the actual instance of the dependency that you want to provide. Anywhere that you want to inject these dependencies and reference them, you get a generated injector class. So typically, this is where your activity and fragments are. They have an injector class, and this has a constructor that expects exactly these types. So looking at the code, let's say we want to provide a very simple dependency here. Dagger is going to generate an app module, which is your module reference, underscore provide dependency factory instance. And let's say you want to inject this somewhere in your main activity. You're going to get a main activity members injector file. And surprise, the constructor here expects exactly the type that you're getting from your factory class. And so because Dagger is handling all of this is all written by the library, you're pretty much guaranteed that this will compile and that the types check out and everything. We'll talk about this question mark in a second. But I want to think about, well, now we have all these providers, right? For a repository or a service or a view model factory, and these are actual objects in memory. So where do they live? Like, who owns them? Because this is object-oriented programming. They have to be owned by a superclass, and this is Android, so it has to be attached to a lifecycle. And we as developers don't really touch these objects. So who's actually managing this? The answer is the component. And the component is sort of like the core logic that hooks up your providers with your receivers, right? Because it has access to modules and it knows about your receiving sites. And your component is going to have a lot of this logic in it, which is really funny because the stuff that we write isn't really that verbose. So typical simple app component, let's say it injects your application class and an activity. Dagger is going to take that and create an implementation called Dagger app component, which is going to have a lot more stuff in it. And of course, if you instantiate your component, typically in your application class somewhere, this is the object you're referencing. So this is why you will probably get a bunch of errors if you haven't built your project before writing this bit of code for instantiation, because you have to build it so that Dagger can write this file and generate it, and then you can reference it when you have to instantiate it with their build functions. So taking a look at your typical component file, it's literally just Java under the hood. As you can see, it's going to maintain references to all the providers that we wrote. So these are all coming from your modules and what have you. These are your provider references. It's going to override the inject function that we wrote here. And so whenever you have, for example, this is specific to a main activity. If main activity is calling inject this on itself, this is the function that executes. And as you can see, it's under the hood, it's calling the main activity members injector file, and it's going to unwrap the provider and pass the actual instance of the dependency to main activity. And this is how main activity is actually getting your injected dependencies under the hood. And all of this code is written at compile time and executes at runtime, because of course you have to actually call inject for things to start happening. Where does the graph come in? Because we know there's a graph somewhere. This is Dagger, it's in the name. And so in Dagger 1, we were interacting with this object graph thing. And in Dagger 2, all of that got abstracted away and we start dealing with components directly, right? That being said, there's still a graph. There is going to be an instance of a binding graph for every component, and this is internal to the Dagger library. And really the whole point is this is where the validation happens. Dagger is going to construct a graph based off of the generated component file, and it's going to validate that all these dependencies that we declared are reachable from where we say they are, and that we're able to fulfill all the bindings that we want. And so, for example, it's going to slot in a missing binding node if you are actually missing a binding or a provider somewhere. And this is where you get your missing binding errors from. The binding itself is just extra information about your dependencies, such as the components it belongs to, the scopes, all that stuff. Again, this binding graph is generated at compile time. So this is what gives you that compile time checking and compile time validation, which makes Dagger such a fun, useful thing to work with. That being said, most of the time as developers, we interact with the component. And the thing is, the component is a Java object just like every other object. If your main application class instantiates a component like this, it's maintaining a reference to the component. And we know that the component itself maintains references to all of the dependencies we declared. So if you think about it, if you think in terms of memory management and performance, the component is a really heavy object. And so leaking components is definitely a bad thing to do. Spinning up and tearing down components is something that has to be approached with care. Similarly, if we reference component objects in your activity classes, you're referencing a real Java object in memory. Managing this component is up to the developer, so it's totally possible to do some very, very wrong things with Dagger and get very unexpected results. For example, let's say in our activity class, we want to instantiate a component, which is fine. But we put the instantiation code in our onResume function, and what this means is that we just keep regenerating this graph over and over again, which ends up being a very expensive function. And also, every dependency that we try to inject, even if they're singletons, are not guaranteed to be the same objects because they could belong to totally different instances of this graph. Similarly, let's say you have two different classes that want to inject the same singleton dependency from the same component, but we reinstantiate the component each time. They're going to reference different objects under the hood. And this is going to be a problem that we run into at runtime because this stuff just compiles, but because of the fact that we don't manage the component correctly, you end up with these really weird errors. So explicitly, the component is going to own all these bindings, and that's managed by the library. The implicit binding, the fact that your component has to be managed by its lifecycle owner, is totally up to the developer. Let's dig into bindings a little bit, because now we know that between the graph and the component, Dagger controls instantiation of objects and also their lifecycle because the component owns them, right? So we can start delegating some of this work to Dagger itself. So we'll talk about the binds annotation, which is the first of multiple annotations we deal with today. So typically, if you want to work with interfaces and provide an implementation of an interface, you would have to write two providers, right? You generate an implementation, and then you pass that as a constructor dependency to the interface that you actually are going to inject in your receivers. Using the binds annotation, you can delegate all that work to Dagger. Under the hood, this is going to tell Dagger to instantiate an impl class, insert it into the binding graph, and then create a dependency edge between this impl instance and the interface that we want to provide. And so all this work gets abstracted away. This saves us a provides function, which means it saves us a factory class. And at scale, if you are managing hundreds of dependencies, as you can see, it probably saves you a bunch of files in the project. We can really level this up with multi-binding. So this means that Dagger can not only instantiate subtypes, it can actually assemble them into a collection and manage that collection object itself. So let's take a look at how this would work. Let's say if we want to inject a set of type T, all we care about in this case are the elements that will belong to the set. So say that our class foo wants to inject a set of strings. Dagger is going to handle the generation of the actual collection object. We just care about defining the elements that belong in this set, which we can do with the into set annotation. And again, because this element becomes a binding in the binding graph, Dagger is able to crawl through the graph and at runtime able to pluck these particular objects and assign them to the set that's going to be injected into your receiver class. And if you have multiple sets of strings that you want to deal with, you can use qualifiers to differentiate between different sets. The same thing works with maps, by the way. Dagger can use the into map annotation, and of course with maps you need to define a key. We're able to define string type keys or class keys. Another thing to keep note of is that these collections are assembled at runtime, and so it's totally possible to get different collections back in different receivers. And so if you're trying to create a singleton object, you'll have to explicitly associate these elements with the singleton annotation. This was a fun example, but really multi-bindings give us a lot of architectural freedom. So let's take a look at how we can actually use multi-bindings at the app level. For example, we have a set of bottom navigation tabs, and we want this set of tabs to be flexible and extensible. So the user could see 3 tabs or 10 or 5. They could see different tabs based on A/B testing or whatever profile they're logged into. We want to be able to make this as flexible as possible, right? So what we really want is to define a set of tabs, and our tab is going to be some information about this element. For now, let's give it a name, an icon, and a navigation route. And the rendering logic has to be decoupled from the logic that's assembling the set. We just want to know, I want a set of tabs and I'm going to render it, right? I don't care if it's 3 tabs or 10. This has to work for any number of tabs and any collection of tabs that you pass in. We can do that by using subtypes of tab. So let's say we want to instantiate a favorites tab. We give it a name, icon, and route. And to add it to the collection, all we have to do is to provide it in the Dagger module using the interset annotation. So between this annotation and the type, Dagger is able to infer that this object belongs in the set that's injected into our tab renderer. And as long as they exist in the same scope, as long as they exist in the same graph, Dagger is able to find all of these objects that we're providing and inject them into the receiver class as part of the set. And so this really scales very well when we have these multi-module, multi-team projects. So very often you'll have teams that are responsible for specific products or specific product feature areas. It's totally possible for them to basically provide a tab by first adhering to the contract interface and then providing it to the central rendering logic using a simple annotation. And this means that we can have lots of people working in parallel, and the logic of combining all of these things into the plugin architecture becomes much more simplified. And I use the word scope, as in like things existing in the same scope. So let's talk about this a little bit. So how can we get more fine-tuned control over how long these objects live, right? So far, we're assuming that everything in the app component, if it's declared at the application level, all the dependencies, the bindings belonging to the component are going to be alive for the lifetime of the app, which is kind of wasteful because what if you don't want that? What if you need dependencies to live only a certain amount of time? There's possibly dependencies that belong to a certain activity or a feature and they're never used at any other point. And if you're thinking about cases where like you have hundreds of dependencies, this becomes an inefficient use of your app's memory, right? We basically want to scope dependencies, which means another annotation, the scope annotation. This declares bindings and binds them to the life cycle of your component. And this basically says if your component annotation and the binding are annotated with the same scope, that binding is going to live for the lifetime of the component. And when the component dies, the binding also dies. So if your activity holding the component goes into its on-destroy cycle, all the bindings are also going to be destroyed naturally, but also you're going to get the same binding back. However many activities share that component, share that scope, you get the same instance of the binding back. And this, again, looks a little magical, but it's really Java under the hood. Basically, somewhere in the component logic, you're wrapping your provider class with the double check class. And this basically takes care of caching the object under the hood. The classic example is really the singleton annotation, which we've probably used. There's really nothing special about singleton. It's just sort of your default scope. There's nothing stopping us from declaring as many scopes as we want and making them behave like singleton. So if we take a simple example, let's say we have a detail fragment that needs a formatter class that nothing else in the app uses. We can declare a scope at any point in our app, and we declare a component annotated with this scope. And the reason the component becomes necessary is because if we annotate the formatter with detail scope and then try to provide it within the app component, Dagger is going to complain because your app component is supposed to be for app scoped objects. So for smaller scope, you need a smaller component. And then however you provide the actual binding, whether it's through a module or just by itself, if we annotate with detail scope, it basically means that this formatter is going to be scoped to detail component. And as soon as detail component is destroyed, your detail fragment is destroyed, all its related bindings are also destroyed. Basically, then your binding graphs are going to look something like this. You have your detail component with a single binding and an app component with however many bindings it chooses to have. And let's make this more interesting. Let's provide the same type in different scopes. And for that, let's go back to our tab example. So right now, if you open up your app, you're always going to get the same set of tabs, right? You can't tell Dagger, I want these tabs for this experience and these tabs for another experience. But that's a very common use case. So what if you want to provide state-specific experiences? So let's say when you're signed out, when you launch the app as a guest, you want to be able to see your news and music tab, nothing really personal. As soon as you've signed in, you want to switch to your personal tabs, favorites and profile. And right now they're all provided under app component, and maybe you can use qualifiers to differentiate between different sets, but then also this gets awkward because your receivers have to know about the qualifiers. And so if we want to abstract that logic away, we can define two different scopes. So signed out scope and signed in scope. The code for this is pretty simple. We just define new components, a signed out component and a signed in component. And when we declare our dependencies, we annotate them with the correct scope that they belong to. And what this means at the Dagger level really is that you're creating two different graphs. You have one graph that's spun up as the guest experience as soon as the app launches, and the only findable tabs to be injected are news and music, because that's the only two that are reachable within this graph. Once you sign in and you instantiate signed in component, and your signed out component is torn down, the only reachable tabs are favorite and profile. And so we're actually really tightly scoping the dependency and the availability, and we're making this a compile time thing. So if you're in signed in component and you're trying to access music tab, you're going to get an error at compile time saying you can't do this. It's literally not reachable from this graph. And so this is great for when we want to have some very specific experiences and we want to scope dependencies very tightly, but it doesn't scale because obviously we can't create two separate graphs for every experience, right? At some point we have to share dependencies. And you can't do that with this graph structure. What you can do is use the subcomponent annotation. And what subcomponents do is they create parent-child relationships between graphs. And what that means is your child components have access to all of your parent components' bindings. So in our case, what we can do is create a top-level app scope, like at your application level, which has a bunch of bindings, and signed out and signed in component can be subcomponents of your app scope. And this lets signed out scope and signed in scope access your top level dependencies without accessing each other's dependencies. Sibling components can't access each other's graphs, but they will both have access to, say, your common retrofit service, for example. And this looks like, again, a bit of Dagger magic, but if we look at the code, interestingly enough, Dagger is only going to generate a file for your top level component. And the way it represents the subcomponents of the parent component are inner classes. So this is all just Java under the hood. Let's say in our example, we have a top-level Dagger app component. It's going to have references to its own app scope dependencies. And then it's going to provide its subcomponents as inner classes. So for example, if you need to inject subcomponents, you basically get your instance from your top-level app component. And your subcomponents are inner classes. They have references to their own dependencies. And when they inject their dependencies, as you can see, they can reference their parent graph's dependencies as well as their own. A caveat here, So as you can imagine, if you have a really deep nested hierarchy of like 4 or 5 parent-child subcomponents, this file is going to get really, really long. And if each of these graphs have hundreds of dependencies, it's going to get humongous. And so this is a warning to say that like this is going to have real compile time performance implications. That being said, there's nothing stopping you from declaring as many scopes as you want. So let's say even in signed in scope, you have a bunch of bindings that are associated with a billing flow, for example, or settings. You can create all of these scopes and design the hierarchy the way that you want your dependencies to reflect. Pro tip, if you end up naturally creating a bunch of subcomponents related to activities, contributes Android Injector is really great. It sort of auto-generates a scope per activity under the hood. So that's worth checking out. Hilt also has great built-in support for this. At the application level, there's a lot of benefits to things like this. You can organize dependencies however you want. This data separation, it really helps when you have mutually exclusive experiences and you want your dependency structure to reflect that. It also helps with some performance and memory issues because you're able to control how many objects are alive in memory at any given time. And it's also great for things if you're providing things like coroutine scopes at a particular level, you can very tightly control where these objects are going and how long they live and where they're going to live. There's also really good reasons to not do any of these things. Just because we can does not mean we should. And so this is the part of the talk where I start ranting because all this stuff, scopes and subcomponents, this is so important that you get 2 means in a row. Eventually, your dependency graph looks something like this. And all your scopes are pointing to each other, and it becomes super complicated. Everybody starts out really small, right? You have like 3 scopes in your app, but oh wait, we're adding a new feature set, so here's another scope. But okay, it needs to share some more data with this other scope. Okay, so we need another level because they need a common parent. And then, oh wait, hang on, we need another scope to fix that. And here comes circular dependencies. And you can fix some of them with lazy instantiation, but not all of them. And so this problem becomes this giant snarled mess. And somebody somewhere, probably me, is going to screw up very badly and have Dagger problems and errors that they cannot debug. And it causes all sorts of subtle, hard to debug, hard to reproduce problems when you have really complicated hierarchies. And then you also have performance problems, probably, especially if you're using kapt and you have these really large component files that have to be parsed at compile time and all that stuff. Ways to limit this complexity is to first not use scoping, if that's entirely an option, or just keep it very, very limited. Another way is to keep the hierarchy as flat as possible. I have found that it's better to have a bunch of sibling components than a really deep hierarchy of parent and children components. Try to be very sanitary with scopes because a lot of this is implicit and it's very easy to leak data or leak threads or inheritance where we didn't intend to, just because it's really hard to parse a Dagger graph. And eventually you have these big code bases where like 3 people in the whole company understand how this works, and then this is where problems happen. There's also Dagger SPIs. We don't unfortunately have a lot of time to dig into this, but this is a great tool for writing custom compile time checks. And so it's possible to write a plugin directly on the binding graph itself. And what this lets you do is write a custom script to parse the binding graph that you have at compile time and write checks for the objects that exist in your graph right now. So we can write rules, for example, to make sure that activities don't inject optional bindings if that's something that you care about, or to make sure that subcomponents can inject certain parent bindings but not others. Again, this is something that can help really codify at compile time the mistakes that we're seeing over and over again. But again, this is a lot of work and it's complicated. And so it's better not to have this problem in the first place. And so this talk was definitely more of an exploration of the fun things that we can do with Dagger. But the thing that I've found is that as Android code bases get older and larger and more complicated, it's really handy to have tools that are equally complex and that can handle this complexity. So I hope that you learned something fun and interesting today. I had a lot of fun digging into Dagger to see how this works, and this was by no means comprehensive, but hopefully something to add to your toolkit. And cool.